All right, John Valvano here. Welcome to the second half of week 3. We're going to talk about arrays. I'm going to do an example from 312H. You're going to have to help me. I have no idea what he meant, but I'm going to show you what it looks like in assembly. So that's the way in which we teach 319K, and C is to show you side by side. And so that is our goal here. I would like to, while we're talking about C, to remind you that when you add two 32-bit numbers, right? If it's an unsigned number and it's 32 bits, how big can it be? No, yeah. Each 32-bit number can go to 4 billion, right? If you add two numbers between 0 and 4 billion, you'll get a number between 0 and 8 billion. So two 32-bit numbers will give you a 33-bit result. And if you chunk it back into a 32-bit variable, you might have overflow. You might have got a catastrophic error. The general rule is if I take an n-bit number and add it to another n-bit number, I get n plus 1 bits. What if I add an n-bit number to an m-bit number? Ooh, how about that one? I'll ask you that one on the test. What if I take an n-bit number and add it to an m-bit number? What do I get? Assuming n is bigger than m, just doesn't really matter, but assuming n is bigger than m, I still get n plus 1, right? So 4 billion plus a 2-bit number could still overflow into 33 bits. The same thing when I subtract two numbers, assuming n were bigger than m, I'm going to get n plus 1. Right? Now, in the ARM Cortex-M, if you set the s, if you add the s to the end of the add, it will set the carry bit on unsigned overflow and the v bit on signed overflow. Your job as programmers to make sure overflow doesn't happen, or at least you detect and correct, because that's a catastrophic error. An n-bit number times an m-bit number is n plus m bits. What about an n-bit number divided by an m-bit number? Assuming the number is not a divide by 0, okay? No, it's still n. So I take a 4 billion, let's just do with 4, I got a number between 0 and 4 billion, okay? Assuming I don't divide by 0, if I divide by anything other than 0, what's the largest it could be? Divide by 1, and so it's still n bits. Okay, so we get a different error on a divide called dropout, and we'll talk about that later. But just to suffice it to say, we do have these general rules about overflow. Okay, so the big picture for today is to talk about arrays. Okay, we're going to do in 319H, we're going to do arrays both with pointers and indices. Lab 4, we're going to do arrays in assembly language. Lab 2, homework 3, we'll do arrays in C. Okay? As a review from last time, what goes in the header file, the .h file? Yeah, what is it called? Yeah, not the define, actually. Define is the implementation. If I define a function, that shows you the code that actually runs. The declaration or prototype is just the output parameter type, the function name, and the input parameter types. That in entirety is a prototype, and they go in the header file. Okay? So in the header file is information about what the function does. Okay? What are its inputs? What are its outputs? How does it work? Okay? What goes in the .c file, the code file? The implementation. Okay? The definition, the implementation. In other words, how it works goes in the header file. And then in most programming environments, we'll add a third file, which the user doesn't ever run, called the test main. It shows you how example use of how to use the functions, how it was tested. This is the file you're going to show to the judge when you get dragged into court and sued for software that killed somebody, you're going, no, seriously, you're going to prove to the judge that you actually tested it. And in the test main, and you'll see that throughout the course, we have these, we write a function, we get a prototype, and then we write a whole lot more functions to test it. Because testing is harder than implementing. Okay? And, all right. Okay. As an example of an array, there's a temperature array here with 1,000 temperatures. Well, they're in units of, say, units in centigrade. There's a heart. We're going to put a temperature sensor in the pulmonary artery. We're going to put a temperature sensor in the pulmonary artery. And we're going to inject a cold bolus of ice saline into the right atrium. All right, here the cold stuff is going to go into the right ventricle, come out the pulmonary valve, go down the pulmonary artery, and you're going to get a temperature curve where the temperature as a function of time will first drop and come back. All that's kind of fun. What you're going to be able to do from this measurement, and that is if you integrate this curve and divide by some constant. So if you integrate the curve, divide by a constant, you're going to be able to measure the cardiac output, the number of liters per minute that the blood is pumping. All that's kind of interesting. Let's get back to C. What can you tell me about this temperature array? Where does it exist? Is it global or local?
It's an array.
Yeah, but is T global or local? Global. So it has public scope. Any function throughout the system can access it. And it has permanent allocation in RAM. Okay. How many bytes does it take?
1,000 times 32.
1,000 times 4,000 bytes. So it uses up a big chunk of your 32,000 bytes of available memory, by the way. But nevertheless, that's why it's not 10,000. Okay. And then what can you tell me about K3? Where does, before you jump into the bushes, think about your answer. Where is K3 allocated? RAM or ROM?
Where? Because it's just a array.
Ooh, you guys are so smart. Yeah, that's the advantage of taking 312. K3 is not allocated in RAM or ROM. What is it? It's a compile time copy paste. So wherever there's a K3, it'll replace it with the characters 4360. Why is it physically there?
To tell the compiler.
I know, but why didn't I just put 43? Why didn't I just put 43? Make it easy to change.
Yeah.
So if I have 25 different machines, I'll calibrate each machine, and each one will have a different number. Okay, but they'll have the same function here. All right. What can you tell me about sum I and CO? Look, those variables. The unsigned 32 bits. The globals are local.
They're uninitialized.
You can ask that question. Yeah. They global or local? Local. Where are they physically? And when you do this, when you see this machine code for this, where would you look for them? Registers. Okay, and they are uninitialized. So you'll see right here that some needed to be initialized, so it's initialized there. I needed to be initialized, so it's entered there, and C just was calculated. Okay. All right. Any questions on this example? It's a bad example of because it uses globals in an inappropriate way. I should have passed it as a parameter. Yeah.
So
question?
this won't be a main. This will be a function.
This is a function, right? So tell me about the function. It's got a name, cardiac output. Now, is it a good function name?
Yeah.
Yeah, because that's what it does. Okay, measures cardiac output. Now, if you were a doctor, you'd know what that meant. Okay, it's the number of liters per minute your heart's pumping. And does it have any input parameters? No, it should have, but it didn't. And it's got an output parameter. Okay. Question? Yeah. Yeah, if you got a he said, so you put local variables in registers, and I says if you can, You do. And so you'll notice that when I do Milos's C program, and he has an array as a local variable, I'll make it a global because I don't want to teach you how to do local arrays. And so you do have, R1 through R12, R0 through R12. You got 13 registers. And so if you've got less than 13 variables, you're probably going to put them in locals. Okay? You have a question?
There anything else be put on the stack then?
Okay, so ask the question again?
Like if you had more than...
Yeah, so if you have more than 13 things or an array, you're going to put it on the stack. And that's lab 7 in 319K. We'll have big arrays and crap we'll put on the stack as local variables. Because it's still private scope, temporary allocation when I put it on the stack, yeah.
So in our Cortex-M, we have 13 usable registers on like a full-scale Windows computer.
Yeah, you've got like 6.
Really?
Yeah, you've got way more than you got on a.
What?
Yeah.
Why is it so few?
Because it's a difference between a risk. You remember the definitions of risk? And now
Cost benefit?
risk. No. Reduced instruction set computer. Right? Very few addressing modes. More or less constant object code. Lots of registers. Okay?
They're easier to work with on our scale.
It's faster. RISC is faster than CISC, complex instruction set computer, where you don't have as many registers, but every instruction's weird. Like, you can have an instruction that says, go to Ocean City and get a suntan. Come back a week later. And that's one opcode. Yeah, like, Could you make the opcodes on a CISC do weird and lots of stuff. And they take, they're fun, but writing 10 short instructions is faster than writing one big instruction. Because you can pipeline crap and you can do things in parallel.
So I thought I read in the book that once you get past registers 0 through like 4, then you have to push.
Okay, so fair enough. I said there were 13. You actually have 4 through 11 that you can use for variables. Okay, in all fairness, you have whatever that is. 4 through 11 are your local variables. And 0, 1, 2, 3, and 12 are actually not, we won't put local variables in them. All right, let's go on. Okay. What I'd like to do with this example is, given you guys are in 312, this is probably pretty trivial for you, but I bring this up because you need to fully understand this example to do lab 2 in 319H, okay? So I'm going to do this example in way more detail than you're probably comfortable with, just so you fully understand it. Okay, and the way I'm going to do it is I'm going to copy paste this into a text editor and convert it to assembly language. Okay, still recording. That's good. All right, there's one. Oh, that's my second one. I'll do that one in a minute. All right. All right, so I'm going to convert this to size EQU 10. As you know, that's not exactly the same because this is a symbol in assembly language which is invoked or created a value. It's not a copy paste. EQU will create a value, but the purpose is still there so that you can create changeable code. Okay, my data, which is going to go into RAM, needs how much space?
4.
Well, look, it's right there. It's an array of size 10, right? 40, not 40.
4,000.
4 times size. Yeah, you get with me? Yeah, sure, yeah, because you can't put a define unless you let the guy change it. No, it's whatever. It's going to go in RAM. Okay. let's look at what happens here. We're going to create a function, call it start. Okay, how do we allocate a local variable?
Area.
No.
Never mind.
Where do local variables go? In a register. How do we allocate a local variable?
Say register.
I don't have to set the register. This local variable is uninitialized, is it not?
We don't do anything.
I don't do anything. I just say, hey, let's put, I just put comment. Put it in R4. Okay? Just with me?
Yeah.
Just my decision. Okay?
Why didn't the comment out the other stuff that you wrote on that?
Oh, because this is Notepad. Oh, I should, if I did this in the Kyle assembler, that might make, the color would, it's assuming it's a C program. So all the colors are weird.
It's smarter.
Yeah, this is Notepad Plus. It thinks it's C. It's not C, it's some of the language.
But I thought it was C.
No, the stuff on the left is assembly. That's what I'm doing here, right? Are you with me? You with me? So, whatever. Okay. To do this, I'm going to need to do the while one, I'm going to need all right, I put in the semicolon just so that to see, right? And then this is interesting here. It's going to take a couple of lines, so I'm going to, last time did I tell you where parameters go? Registers, right? So what is the type of my data? When in C, when I use my data without the brackets, it's a pointer, right? So all I got to do here is LDR R0 equals my data, okay? That's the first parameter, okay? And the purpose of my madness here is you're going to understand one of these two better, and you can use the other to figure out what it is. Okay, so how do I get the size into R1? Move it. Okay? How do I call a subroutine? No, BL. And then we call the name of the function max. All right?
And the L, that does the return register, right?
Yeah, that's it's R14, the link register with the return address. Okay?
And so the B is just unconditional branch. What would you call that?
This is a subroutine call.
So
BL is a function call. Branch with link? I don't know. That's what the BL stands for. Is that good? Yeah. Yeah. Where's the return result?
R0.
R0. So to put it into my max, I'm going to have to do a move R4, R0. So now my max is set. Okay? For whatever purpose it is, right? And then I'm going to do a branch, unconditional branch. Yeah, come back here. Yeah, see? No. Yeah, see? No, okay. Okay. Branch to loop. All right? And then obviously this is my notepad getting all weird about the C. All right. Questions on the invocation of a call by reference? I passed the whole array in one register. Okay. Let's go back over here and capture this. All right. All right. So to implement this, I'm just going to need a label for my function, and I'm just going to have to know that R0 is data and R1 is size. Okay, that's the word. Notice this is a lowercase size, not an uppercase size, because this is a copy of the size. It's not the size, it's a copy of the size. On the other hand, R0 is not a copy of the data, it is a pointer to the data itself. Okay, so it invokes a potential, potential security risk, by the way. Right? It does. Having a pointer. You've got to there's an inherent trust between these two functions. Yeah, that main trusts Max to not write crap into your array or throw your stuff away or give you extra money or whatever it is you don't want it to do. Okay. Now it turns out, according to ARM Architecture Procedure Call Standard, if I were to use R4, I'm going to have to save and restore. So you remember the rule was I want to put answer in I into registers. And I have two choices. I can put it into R2 and R3, or I can put it into R4 and R5, depending upon how complicated I want to be. Okay, so let me put it into R4 and R5. And then in order to put it into R4 and R5, I got to save them. Okay. Is the local variable initialized? Does this line of C code initialize the variables? No. Just if we're global, it would have. Locals are not. So R4 got whatever crap is in it. Yeah.
So that's pushing R4 and R5 to stack, right?
Yep.
And so is it doing R4 first and then R5?
Doesn't matter. R4 is on top. R4 is on the lower address. So you sort out the register. It's irrelevant what order you type it. The registers are stored such that the register number, as the smaller register number, as is in the smaller memory address. 32 bits each, 4 bytes. So that will subtract 8 from the stack pointer as it pushes. All right. So this one's fairly easy. I'm going to set load. Oops, I want to put it on the other side of the load. Sorry. I'm going to execute. LDR R4 bracket R0. Okay. So what was in R0? A pointer to the first element of the array. What was the type of the array? 32 bits. So I use a load instruction, and I'll fetch the first element of the array. Okay. This one takes multiple steps, so I'll leave it there and write it this way. How do I set I equal to 0? Move R4 pound 0. Okay. In a for loop, what happens second? The check. Okay. So now I got to do a compare which number it is, R5. I'm going to need a label here. Just saying, I'm gonna. Yes, of course it is. Thank you. Yeah, and I appreciate you talking at me before we get to the end of the class. Thank you. Typo. Yes, thank you. Am I better?
Yeah.
Yeah, better. Good.
Do you already have a loop?
Okay, fine. Loop 2. Thank you. It would have not. I can't have 2 loops. You're absolutely right. R5 to R1, right? R1 is the size. Okay? And so I want to quit if it is greater than or equal to size. Okay? And I got to know whether they're signed or unsigned. Somebody help. The size signed or unsigned? Unsigned. So I'm going to use an unsigned compare branch high same to quit. Right? Just some label further on.
Wait, what is BHS?
Branch high or same. Yeah, it's only about 30 instructions you got to memorize, and this is one of them.
Branch higher same.
Branch high or same.
Can you do
Branch low same, branch low, branch low, branch high, branch equal, branch not equal. How's that?
So compare automatically does the conditional?
Yeah, compare. It does the subtraction without just setting the conditional bits without affecting the registers.
Oh, okay.
So will branch if R5 is greater than or equal to R1?
Yeah.
Okay.
Yeah, high same. If it's higher or the same. But there is a greater than or equal to for signed numbers.
So
GE. There is, but these are unsigned. Are we with me? They are unsigned.
add like a U for unsigned?
No, I can't. You get to grow up, make your own instruction set. All right, you with me? All right, so I++ occurs later. Next is the body. Right? Next is the body. So now I got to fetch the ith element. You remember the rule about fetching the ith element? What's the formula?
Size plus,
I is in, right? I is in R5.
R0 plus I.
No. R0 plus 4 times I. Sorry. So I need another register, logical shift that way. Left, I guess. R2, R5, pound 2. That's times 2. And now I can fetch LDR R3, R0, R2. Okay, so I just fetched the ith. Okay? With me? And I'm going to compare it now to, the thing I just fetched. I want to do it in the same order. I've just fetched R3, and I'm going to compare it to R4, which is my answer. Okay? Now, here's a trick question. Is the data signed or unsigned? Signed. Okay, so it turns out this guy looks like that guy, but I'm going to do, okay, so I want to skip it if data is less than or equal to, okay, branch less than or equal to, what happened? No, I go over here. Branch less than or equal to, not now, or not something, okay? All right? And then here, if it is true, I'll do a move into R4, the R3, okay? And then this is going to be not now. Not now, and then I'm going to do I++, add I is in R5, pound 1, okay, and that's the I++, and then branch, unconditional branch, 2, loop 2, all right, and now I need quit. I need quit. And then not quick sort. I don't want that. And then I'm going to return answer. The answer is in R4, right? So I got to move it to R0. That's a rule. Okay. Then I want to, I moved it so R4 is no longer needed. Now I can pop the registers off. And again, it don't matter what order you type the registers in. It pops it such that the smaller register number is at the lower address, and then we do a BXLR. Okay. Right. What is BX?
That's the return.
Branch through a register. That's the return from function call. Yeah, question.
Is it convention that you return the return variable this $0?
Yeah, so there is a convention. Yeah, let's see. It's actually got a name. It's just got a name. ARM architecture. I can't spell it. Architecture procedure call standard. And, R0, R1, R2, R3 are the inputs, and R0 is the output. Okay? That's a standard. Okay? All right, so again, I'll post this file here. You'll see it on the web as feb6.c. Okay? But at this point, in order to do Lab 2, you really got to fully understand this example, okay? Because Lab 2 is much more complicated than this. So any questions on how this works, either in C or in assembly? Yeah, question.
Can we go back to the program?
Yes.
And there was this one point where it's like LDR, I think.
2 brackets.
Yeah, with the brackets.
2 registers.
Hold on.
and a bracket.
Did I type it? Make a typo?
No, you make a typo.
Okay, give me a line number.
there. 25.
25.
It's just an instruction. That's hard to understand. It's not
Hard to
like-
understand. What's the only addressing mode? Look at line 25. What's the only addressing mode you can use with a load? Load R. The only one. Register. Indexed. Okay? So every load R has got a bracket. And inside the brackets, the square brackets, is an address. Okay? Now even when you type equals, right? As you know, we did this a couple of weeks ago. Even when you type equals, this is an indexed addressing mode with the program counter. Right? That's how that gets compiled. And so this is an address. It adds the two together.
Okay.
How's that? Is that fair?
So why was that helpful in this case?
Because I indexed into the array.
Because the size times
'Cause-
4 plus
Yeah, you see, I is not a constant. I is a variable. You see?
yeah.
I is a variable that's in R5. So this address right here is the base address plus 4 times I.
And it doesn't set anything, right? If you
This doesn't change R0 or R2. It does change R3, obviously. Okay? Let me ask another question. What is the only instruction that you can read from memory with? LDR, with the B's and the H's and the S's and whatever. The only thing you can read from memory with is a LDR. It turns out, even if you guys are excited about this class, okay, that is a memory read instruction. And it's actually a load R instruction. Just with more fancy crap that would kind of be fun to look at sometime when we have more time. That's actually a load R instruction. It's called it's an LDM. It's a load multiple. And this is, it wouldn't surprise you to know, is a store instruction, ST instruction. Store multiple. All right. So again, in order to do lab 2, you got to fully understand the C. I invoke my assembly privileges because this is 319H, and I think it's meant to help you explain what it is Callbyreference is. Okay? So there are 10 elements in the array. How did they get passed? As a pointer. I didn't copy 10 numbers. Okay? And when you get to Java or C++, you're going to want to know, especially if your array is 10,000 long, how it is it got passed. Because if you call by value something that's big, you're going to have to somehow make copies of the data and pass them one by one. All right? So, all right, enough of that. Okay, so let's do another one. This one's fairly easy. Yeah, so dot product. Well, I don't know if it's easy or not. This is a way. If you look at the first parameter, what is the type of A?
signed integer.
No, it's actually not a signed integer. The type of A is what? Okay, you're getting closer. A pointer to an array of signed integers. Okay? So when this gets compiled, what's in R0? The address of the array. Okay? The same thing with B. Okay? What about length? Where's it? And register which one? R2 as a value. Okay? So if you were to, let's go ahead and, let's see, what should I do here? I don't know. This one's so much like the other one. I don't want to show you the assembly code. Here's what I can show you. What about this? Okay, so how did I specify a call by reference parameter when I define the prototype or the definition of the function?
Create a
what syntactical element that I add to the parameter data to define, specify that it's going to be called by reference, a pointer to stuff, the brackets. Okay. Turns out there's another way to do it, and I don't know if you like it better or not, but I'm going to show it to you because that's the way we roll in this class.
Wait, how do you like
Huh?
do like block? I don't know what's called.
Okay, can I? Don't go away. Can I just finish my thought here? The other way to pass a pointer in C is to define it as a pointer. Now, I know you've seen this because I've been trolling your 312 website. Okay, so the line that's commented out and the line run underneath it are identical. Okay, in both cases, you don't really know how big the array is. It could be a single variable. Now, obviously, it wouldn't be in this case because I passed the size of the array as a third parameter. Okay, and you wrote both you wrote both the implementation and the test of it, so you know that A is not a single 32-bit signed number pointer to A. It's not a pointer to a single, but a pointer to a bunch. And so this exact syntax right here, okay, with this definition will still work. So if A is a pointer to a 32-bit number, what is A bracket I?
A plus 4 times I.
Dereferenced. It is the contents of A plus 4 times I. Okay? Just like we did in the previous example. Okay? Again, just like this example, we could have, we didn't, but we could have. We can't have them both, obviously. All right. Those are exactly the same syntax. So if you pass a pointer, you can access the data at that pointer using the bracket syntax. Yeah.
Is that just because it's an array? Like if you were passing
No,
the int, would it be passing the pointer of the int?
Oh, no. Look at size. We did size already. Without the star, size is a value that's copied and can't be dereferenced as an address. Okay.
And now it could be at a new address, right?
Well, I could call this function with other data, right? This function can be invoked with other arrays of other sizes.
So it copies size into a new address in the new function?
No,
Like if
copy size, the capital size, which is a 10, is copied into register R2, R1. And within the function, the size in here is a copy of the size. That's the difference between call by value and call by. Remember we tried to flip two last time on Tuesday. We tried to flip two things with the call by value. It only changed the local copy and not the original one. But with pointers, you have access. So in this context here, I could have written to the data. I didn't, but I could have.
So doing a pointer is like as if you're treating it like a global variable? Because you're actually
Okay, it
affecting
doesn't.
the
No, not necessarily. You're sharing the same.
Okay.
So if, for example, in most of your 312 examples, he would have put my data as a local here. So call by reference means that the caller and the callee use the same data. Call by reference, because it's a pointer to the data, not a copy of the data. That's a very important distinction to make. One is fast as one is secure. Got 10 things, it's faster to give you a single pointer. It's more secure for me to copy 10 things to you and give you a copy. And you can't mess up my original. Is that an answer? Yeah. Okay. Okay, so that's that one. I want to get to, yeah, it's fine. What else do you need to know in here? Anything in here you don't understand? Again, this is similar to lab. It's two arrays. Can overflow occur in this function? Sure, in two places. It can occur at the multiply, and it could occur at the plus. Okay, and I've done nothing to protect my users from overflow. Okay, if I wanted to protect from overflow, what I would have done is made S a 64-bit number, and then after I multiplied the two together, I'd have checked to see if it fits within 32 bits before I added it. And then after I added it, I'd make sure it fits into, and I would be able to detect whether or not this thing overflows. Here's another thing that happened last time. Is this safe from a stupid programmer? No, because as you know, we only got 32K of RAM, and size is a, right, 32K, right, that's only 15 bits. Length is a 32-bit number, and length is negative. I don't know, what's up with that? You know, it's so if you pass in a -1 and something stupid's going to happen. Actually, -1's going to be fine. -1 will quit right away because this is a signed compare. But 2 billion will take a long time to execute. And I noticed that your 312 instructor, Milos, is very good about writing code that stupid people can't crash. Okay? I mean, he's a full-fledged software engineer, you know, to learn from the master. Okay? This example here shows you something very powerful about call by reference. And if I were to ask you, what is the, okay, I can't double click on it, so let me quit that. If I were to ask you what this is, let's go through the mental note, okay? Is the parameter called by value or called by reference? Reference. It's in R0, a pointer to a character string. Okay? You with it? Is it an input or an output? Yes. 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 It's both an input and an output. Because it's called by reference. So you're faced with a problem that needs two output parameters. That seems like a short step from having one. What if I need a function that returns two numbers? I'm going to have to use at least one of them as a call by reference. Okay? And that way I can output one number, 2, 3, or 10,000 numbers using a call by reference. So if I can set an array, fill it with nothing, call a function, and let the function fill the array. Yeah.
So if you did want to pass an array in, like not by reference, like what's the other?
You can't. This is C.
There's no, okay.
Yeah, you can't. I mean, I could do character bracket 0, comma, character bracket 1. I mean, I can do str bracket 0, comma, str bracket 1, comma, str bracket 2. I could do that.
Wouldn't be reference.
That would be value. What?
You have to pass value.
Yeah, I have to pass each value, but it would be safe. It would be safe. In this case, it wouldn't work because I want to uncapitalize the names. Okay, so for example, if I were to call, I don't have my main program. Where's my main program? Uncap name. Okay. So all right, so when I invoke when I invoke the name of an array, what do I get? Without the bracket, right here. Without the bracket, what do I get?
You just get a prototype.
When I have an array, like look at name, right? Name is an array, 10 characters long, having the ASCII string Jonathan in it.
You get an error.
No, I don't. I get a pointer to the first element. I get a pointer to the J. What? When I just type name without any brackets.
What happens if you put brackets?
Well, I'm going to get a value at that index.
But if you don't put anything in the
Yeah,
bracket,
you'll get a syntax error. Now,
or you put a star.
okay, now you don't want to put a star in front of name. Okay, there's a bunch of stuff you could do that works and a bunch of other stuff that doesn't work. Okay? Yeah. Pointers are kind of fun and mysterious. You can put 2 stars and double dereference pointers to other pointers.
Oh,
But
list.
yeah, so you're going to see them you'll see them in 312. So this is going to pass me a pointer to the so let's do, this will be fun. Let's do this guy right here. Let's do this one in assembly. All right. Is this in RAM or ROM? It's in RAM, right? There's no const in there. So it is a variable in RAM, a global thing in RAM. So you're going to see when it invokes, it's going to look like name, lowercase name. Now, in my syntax, I probably should have used uppercase name. How many bytes do I need to store it? How wide's a character? Not any of this Unicode crap. 8, 1 byte each, so it just need 10 spots. Okay. Now it turns out in pre-main, after the reset and before I get to main, it's going to copy that string in there. It'll make a copy of Jonathan in ROM, copy it into the RAM version. So once main goes, the first letter of this thing is going to be a J. Okay? It's going to pre-populate it. And so let's do this one first. All right, so this is going to be start. This one here is going to be LDR. How do I get a pointer to an array of, bytes? Kids get this trouble all the time. What opcode do I use here to get a pointer to a byte array?
LDRB?
Not LDRB. What's in R0?
32, the address.
What is in R0? It's a Callbyreference. Didn't we just know that? That's an address of the. This can't be LDRB.
Because it's 32 bits.
It's a 32-bit address. Even though it's a pointer to a byte, the pointer is still 32 bits. All right? Yeah, so, and then the branch link to uncap. All right. And then all the other crap. Let's go up here and do this one, where you're going to put uncap. Just for my own sanity, it's faster typing. I'm going to go ahead and put this local variable into say R12 or something. R12 is one of the registers I don't have to save. Okay, so I allocated a local variable and I initialized it to 0. All right. In a while loop, what happens first? I got 2 things. I got the test and I got the body. What happens first? The test happens first. Okay, so those of you that don't like me having more than one loop, I'll have a loop 3. All right, so now comes the tricky part, okay? Or the wonderfully great part. LDRB, Again, some register that I can use and not mess up. Where is the pointer? R0. Where's my index? R12. What is the formula? Right? What is the formula? And that is base plus I. Why is the formula base plus I? And the last time it was base plus 4 times I. That's a byte array. Okay, so we're good. Okay. So now I want to compare. While loop is looking for what? A 0 or a not 0. Now the load instruction doesn't set the condition code bits. You can't put an S on a load instruction. It's 0, so you can't. So compare R2 with #0. I can compare it with 0, and if it's equal to a 0, that means it's false. To quit 3. So I'm past the while, and now I got to do the str. The data that I had is still there in R2 because the compare didn't mess it up, and so I do an or R2 #0. That just flips it from lowercase uppercase to lowercase. If you've memorized your ASCII tables, you know how that works. If you haven't, you'll just have to take my word for it. That does flip it to uppercase. But I have to store it back. This is the one that's unsafe. This instruction right here, strb, this instruction here is the unsafe one. Because I'm writing back into the original array. Okay? And I actually made one typo. Is our character signed or unsigned? Yeah, I can flip 50-50, man. 50-50. It turns out there's a button in the compiler that tells you which it is. So you go here, you go down to C++, and right here it says plain char is signed. See that? I didn't make it up. Read and weep, man.
Yes, negative chars. Let's go.
Or the anti-chars.
Yeah.
Anti-chars, exactly.
But it's actually going to get into trouble when we get to lab 10 because I'm going to make you write your games in Spanish.
Why?
Or Portuguese or French or your favorite thing. And we're going to use the second half of the ASCII table for the Spanish characters. And we're going to have to unclick that button so you can actually use the rest of the characters. But today it's not. Today it's signed. And so this actually should have been an LDR-SB.
So you choose if it's signed or unsigned?
Yeah, that's actually one of the reasons we don't like char, is it's not defined as a standard. Okay? That's why we like C99, because everybody knows whether int 8 is signed or unsigned. It's got no U, so it's signed. And that's why we don't like char or int or any of those other C things, because it's unsure.
In our test, like our test 2 when we have to program stuff.
Yeah, this is going to get you.
Can we change it with the settings to unsigned?
You won't have to.
No?
You won't have to. We will not be so mean. You could, to answer your question. Right, okay, so let's do an easy one. I++, as you know, I is in R12. And then unconditional branch to loop 3. And then we need, quit 3 right here. How do I return of nothing? You see the type? There's a return type of void. So what do I put in R0 on my return? What's nothing? No, not 0, 0. That's not nothing. The question is that this function, uncap, has got a return type of void. When I, you can't not return, it'll crash. How do I can't return a null. Null is something.
Just put back what was in R0.
No, don't put it back, just return.
What?
This is what this is. I'm just fine. It's time for you to know how crap works. You just return. Don't whatever's in R0 is irrelevant. You don't have to restore it. Okay, that's a return without a parameter.
The B with 3 shouldn't that be branch equal?
Wait.
The,
Oh yeah. Thank you. You're smart. Points.
I've been saying
Points.
that the past like 5 minutes.
Points. Yeah, no, I appreciate branch equal. Absolutely. That's why, what is harder to do, write programs or test them?
Yes.
To know, testing is way harder than writing. Anybody can type crap. Making it actually work is the hard part. Yeah, of course. Thank you, by the way. Yeah.
Do we not use a stack like last time?
I could have. You want me to use the stack? Because R12 is a free variable. I don't have to save and restore it.
Okay.
Right?
But if we had like more variables, we would have.
If this function called another function, I would have put it into R4 and saved and restored.
And that's like based on your, as a programmer, you have to decide that.
No, as a human he said, is that something you decide? No, that's part of the ARM architecture procedure call standard, how we use registers. R0, 1, 2, and 3, and 12 are free to use however you want. R4 through 11 have to be saved and restored. It's not a lab 3 thing, so I'm going to go on. Okay? And again, I'm going to upload this to Canvas when I'm done. Let's do it a whole nother way. Yeah. Okay, so what can you tell me about the uncapped 2? Let's change it to uncapped 2 so you guys don't yell at me. Okay? What can you tell me about the way in which the parameters pass? We'll start there. The way the parameters passed. By reference. Okay, we did that a couple of slides ago. That parameter and this parameter are identical, except there it's called str and down here it's called p. Okay? And I use the letter p when I mean pointer. Right? I'm just saying. Okay? But the prototype for these two functions are identical. So they could both be called by the same invocation. Right? But it's not quite the same. So let's decode it into assembly language. We can decode it, and now you can ask, what is faster? It's going to be a trick question, by the way. Okay, uncap. All right, uncap. You know where P is? Where's P? In R0. Okay. How do I dereference a pointer? Right? This is LDRSB, pick a favorite register. I don't want to mess up R0, so I'll put it in R1, bracket R0. Okay? I dereferenced that array. Okay? With me? I dereferenced it. Okay, and then, okay, that's a comment. I can put this on here. I got more. I still got to do the compare R1 with #0. This time I'll get it right. Branch equal to quit 4. I'm gonna need a label up here, by the way. I'm gonna need a loop 4. Yeah, I'm gonna need a loop 4 up here. All right. How do I set bit 5? Or it's in R1. It's in R1, and I want to, send bit 5, 0x20. How do I store it back? SDRB, again, R1, bracket, R0. Anybody a little bored?
A little what?
A little bored? Kind of slow today? Yeah, okay, fine. Let's teach you a new thing. #1. Post increment.
Yeah. Okay.
Post increment.
Wait,
So
why?
it adds 1 to R0.
Yeah, why it's 1 to R0.
After it's
After it's done it.
Yeah.
So it's not a pre-decrement or a pre. All right?
Right after?
Yeah, so it skips an instruction, runs faster. Right? Because that's the way we roll around here. Speed. All right. Those of you that aren't bored, skip it. Just add 1 to R0 and you get to the bottom. Okay, so branch to loop 4. No, it's way faster.
Well, like computation wise?
Yeah, how about how long is this? Okay.
Looking at the previous
Yeah, okay, fine. We're gonna do
big O.
yeah, we're gonna do a big O on it. Yeah, we will. Those you need a quick 4. Yeah, fine. We'll do big O. You guys got O's on your quick 4. BXLR. All right. So when you got 2 things, you can go which is better. So let's count instructions. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. 1, 2, 3, 4, 5, 6, 7. Okay. Yeah.
Yeah, but the compiler
The compiler might actually convert that into this.
Yeah.
This one may not be that smart, but if you get a good enough compiler, it actually could generate the same code. Yeah. So. Okay, so somebody said, he didn't actually talk about big O yet, did he?
No.
Did you talk about complexity? What order is this? What order is this? This is N. This is order N. Okay? And both versions are order N. Okay? Linear with the size. If N is the size, it takes, because when this executes, these instructions between loop 4 and branch 4 are going to be executed N times.
Yeah.
Okay? Where N is the size of the array. Okay? And not N squared or N cubed or log N.
Log 2N.
Yes, question?
So the LDR signed byte, why are you doing it signed?
Because that's a rule with this particular compiler and this particular setting on this particular compiler, chars are signed. Now they're ASCII, so they're 0 through 128, so it wouldn't have mattered. Did I answer your question? No, I'm just being completely. All right, I got more. I haven't got to the fun one yet. Understand this? All right, so you guys gonna have to help me out before I get too far down the rabbit hole with this. Okay. What in the H was he trying to teach you here? I hope it was, don't ever write code like this.
What?
That's what change a variable
That's what he
without
does.
ever talking to that variable.
Okay, fine. So don't ever do that.
Why?
Oh yeah, no.
That's what would work.
No. Before we put programs in ROM, you know how we got out of a loop? We would increment the opcode. And would change the opcode from a branch always to a branch never, and we'd get out. So you are not the first one, Milos is not the first one to write code that nobody can understand. So I would just contend that this is bad code and you should never do it. But if he's trying to teach you how stuff works, the other trouble is you're not sure whether it modified A or array.
But we searched, we print out.
Yeah, for that particular program you knew, but when it gets to my program, you don't know. Yeah, it's not, because something weird would happen, if it might align it to some number and actually modify nothing. Sometimes there's gaps between the variables. Yeah, so as long as you understand that that's bad code, I'm happy to show you. The other thing, again, because this is 319K, we haven't got the lab 7, I've moved the 3 variables from local to global, just so that I can write code for it. Okay?
He hates global variables.
Oh, he does, and for all the reasons that you should. I agree with him 1,000%. It's just that I haven't, how do we teach everything? Yeah, he's totally right.
So why are they so bad again?
It wastes. You only got 32,000 bytes of RAM. Right? Just go down that route. If every function in your computer used global, you'd run out of RAM. Right? And if you really only need it temporarily, everybody can use the same RAM by putting it on the stack or using registers. It is really slow, right? Because it turns out if these were local, A and B would be in registers. It's going to take 3 instructions to set A equals 0. Well, no, 2. It's 3 instructions. Get the address, put a value in the register and store it. So globals are slow and wasteful. And they're also unsecure. So you don't know who can access it. Yeah, I can throw a static in front of it and make it more secure, but it's still slow and wasteful. Okay? With one exception to Milos saying never use globals, when we have multi-threading, main program and an interrupt service routine, and you want to pass data from one thread to another thread, you must use a global. You can't put it on a stack. You can't put it in a register. So when we get to interrupts, we must use globals for communication between threads. Because in regular programs, you just, when you want to pass data from one program to another, you use a parameter. Pass it that way.
But interrupts different.
Interrupts have no parameters. They come in the middle of the night. You don't know when they happen. You don't know what they do. You have to put stuff in globals. All right, let me go ahead and I was going to do this in assembly language, but I already did a couple in assembly language. Let me just show you what it looks like in Kyle. Okay, so quit this. Okay, did I already put it there? Globals, locals, no, I haven't yet. I don't think I have. Prime numbers, that's on the 3. I put up, okay, no, let's put it up here. All right, so now I got 2 mains, so I got to get rid of another main. I got some typos. Okay, let's get down here. Let's get rid of this other main. I got 2 arrays. Redefinition. Okay, I got 2 arrays. I got 3 mains. All right, let's see how we doing here. Main. Okay, there's a typo here somewhere. Source code is not. Oh, okay, fine. Oops. It's got some non-printing characters here. All right, let's see if it compiles. Oh, yeah, there we go. Okay, so the difference, in this case here, whether these were local or global, they were initialized because they were specifically initialized. When is A set equal to 0? In this particular example? Between what and what? Between reset and main, it's set to 0 in pre-main. Okay? The same thing with B and the same thing with array. Okay, so so global. Okay, build. Yeah, I can debug. One of the advantages of globals is I can watch them. Add A to watch window. Add B. This is way better than doing this in assembly language because it gets the type.
Can you edit the value to whatever you want?
Can you edit it? Of course, but that doesn't help, does it? Okay. Add. So I've added the 3 global variables to a watch window. Okay. Since I am at main, you can see that they are initialized. Okay. They're all 32-bit values. So this syntax does what? When there's a star in front of a pointer, and the star and pointer is on this side of an equal sign, what does it do? Dereferences with a store. Okay, so a value over here is stored into this element of the array. Okay? Let's look and see how it actually works. Okay? What do you suppose the move S instruction does? Right, we're doing this line 33. Look at the move S. What does it do? Sets R1 equal to a 1. That's the value. What do you suppose is in R2? A pointer to the array. Okay? What do you suppose the store does? Puts the value R1 into the array. Okay? I'm just saying that's what it does. Let's do step over, and you'll see it's there. Let's do this other one, okay? This is now moving a 2 down here. Oh, I want to step over, yeah. Moving a 2 right there. Moving a 2 into R1. And what does the store do? Why is it plus 4? It's the second element is 4 bytes away. All right. Where did it put PA? Can you see? PA would be over here if you wanted to look at it. Okay? But where did it put it? Can you see where it put it? Where do you expect to find it, by the way? Okay, this compiler tricked me before. Where did it put PA? Look at the machine code it created. No, look at the machine code it created for line 35 and 36.
Oh, ignore that.
No up, it's gone. Because he's never used it. It said, bad person, you typed code that didn't actually need to be executed. I shall take it away from you. I'll leave you a no up there if you want a breakpoint on it. But it took it away. Yeah, let's get down to A. All right. A got over here. You saw A got stored with 77. Okay, one more. A got the set one more. He said. Oh, I'm executing single. There it is, 77. If you don't like hex, you can get rid of the hex and see the 77. All right. And then here's the dereference. We'll see which one. Okay, so it's going to store through the pointer and change A. All right, where are we? All right, so when you did 312, which variable changed? A. So we'll see which one changed here. Yeah, 99. It changed to A because they were in the same order. Okay, so summary-wise, the big deal about Lab 2 are arrays, and the big deal about 312, the hardest thing you've got to do now is grapple around pointers, because once you understand pointers, I think your code will go very quickly. And if you want to use your Cortex-M to understand how pointers work, again, you can type stuff in here and look at what it does. Okay, because right there in this particular code, R2 is a pointer, and that's R2 minus 1. Well, minus one thing, which was a minus 4. Okay? All right. Well, we'll see you. Have a good weekend, and I'll shut off my recording. Take care. Bye. I think. Yeah, I reckon. All right. Stop.